Hi everybody, welcome to another up-to-date TWF arcade repair video. This is the second part repair of a Microhard Ripof board set that is a clone of Cinematronics Rip Off arcade. If you haven't watched the previous video, you can find a link to it down below in the description. This board set was completely repaired and worked for a few hours. Then something happened and the logic PCB died, showing the glowing LED of death, meaning that it couldn't correctly execute its code anymore. I haven't caught on camera the failing event since the board set at that point was in the final observation phase after all tests showed no obvious faults left. Notice that I disconnected all connectors from the logic PCB as soon as it stopped working. This is very important, especially for the digital video output connector, since a malfunctioning logic PCB can still output bad vector data and potentially damage the vector monitor. If you have watched the previous repair videos in this series, you know that the Vector Beam Cinematronics black and white arcade games didn't use any of the single IC CPUs available in the late 70s, but their designers chose to make their own 12-bit CPU using something like 80 TTL logic ICs. In fact, almost all of the ICs in this logic board layout are the so-called C-CPU. Troubleshooting such a logic system can be usually more difficult than a classic integrated CPU one. However, I always start from the basic checks, like the 5 volts rail. And 4.7 volts is definitely too low. Yeah, there must be something almost shorting the power rail. Let's measure the resistance. And yes, 13 ohms between 5 volts and ground is too low. Of course, I've checked if NEC was running too hot, and both L11 and N11 were burning as soon as power was applied, so I've just removed them. And indeed, they have many pins shorted to the ground pin. That's very strange. By the way, both L11 and N11 are part of the 12-bit data selector that goes to the CPU magnitude comparator, composed by L9, M9 and N9 ICs. Such a large failure is very peculiar, so let's check the only surviving data selector IC. Well, there's pin 15 showing low resistance to ground. But no other pin of this IC looks bad. So let's see what drives that pin 15 of M11. We need to go to another schematic page to find the S2 signal, and it's coming from a 74S32 gate in position B14. And indeed, B14 showed many pins with very low resistance to ground. I decided to remove it, and indeed it showed many shorted pins, like the other failed ICs found so far. Also notice that the failed IC is a 7432, but according to the schematic it should be a 74S32, and the speed difference between the two families is quite relevant. I didn't find any other shorted line coming to this IC, so I decided to just install a good replacement in B14. So far we have found 3 dead ICs on this board, and all from a single failure event. Before installing L11 and N11 replacements, let's check again the resistance on all pins. There are still some lines that show about 100 ohms to ground, which is too low. I have found low resistance to ground on pins 13 of both N11 and L11. These are driven by pin 2 of S13, which is the ROM data latch. Let's inspect this IC. And yes, a few pins have too low resistance to ground. I removed this one too. Let's check this LS377. And yes, again, some pins have low resistance to the ground pin. So far I've found 4 failed ICs, and all of them were connected together in some ways. I thought about some power supply failure, but I can exclude this, since I'm using the actual power supply of one of the cabinets, and that has been completely serviced at the beginning of the repairs, and never showed any issue anyway. So again, let's check if any of the lines coming to S13 IC shows evident problems. Yeah, pin 3 shows 27 ohms, not good. Now, pin 3 of S13 is also connected to pin 3 of T13, which is the ROM instruction latch, and it is driven by pin 12 of U11, which is part of the ROM even odd data multiplexer. Luckily, if I remove the jumper block in position U14, I can interrupt the path to U11 and see if the short is on T13 or U11 itself. So, jumper removed. And there is no short anymore on the latches side. And on pin 12 of U11 we have the bad 27 ohms, so it must be removed. And yes, it's damaged. Let's update the failed situation. So U11 drives S13 and that drives L11 and N11, but also B14 drives an input of L11 and N11. Maybe we have a pattern. At this point I want to check the 5 volts rail without installing replacement ICs on their sockets. The voltage now looks good, so it doesn't seem we have any more low resistance short at least. Before installing the replacement ICs, I've checked again the resistance to ground on all the lines coming to the failed ones identified so far. And the line L8 shows low resistance to ground. However, there are a few input pins driven by the failed L11 on 3 different ICs, N6, M9 and R13. So I decided to cut the pins one at a time to see what IC failed with the internal low resistance. Here I cut pin 1 of M9, but it wasn't its fault. And here is pin 13 of R13 also cut, but again R13 showed no issues, so the remaining IC at N6 must be bad, and I'm going to remove it. And in fact, pin 1 shows the usual low resistance to ground. So here is the updated situation. N6 is one of the 3 arithmetic logic units and it's driven by N11, maybe a big cascade failure event. Of course, after removing this IC, I've again checked all pins taking note of any issue, but in this case I've found no evident problems. So here I've decided to install a replacement IC and look for any issue with power on. Nothing seems to get hot. Maybe at this point it's safe to install all the replacement ICs. And here we are. Let's power on. Well, the board is still dead. The LED didn't go off. But at least nothing is getting hot anymore. Starting again from the basic checks, I found there was no master clock, and you can easily understand why. Now, I don't really know when the crystal pin break. It might have been during all the board handling to remove and socket all the broken ICs found so far, or it might also be the initial failure that originated the cascaded IC deaths, but it's hard to find a definitive answer. After replacing the crystal, the board is still dead, but we have a clock. When checking again around the failed ICs, I can see an invalid lever on pin 15 of L11. And pin 15 of L11 is driven by the signal DS3, which is generated by the TTL prom in position C14, so I'm going to check it. And unfortunately, the programmer even refuses to verify its content. So let's just burn a new one. Here is the updated failure map, again an IC related to either N11 or L11. At this point I took the time to verify all checksums of the code EPROMs and all the other TTL proms, and I haven't found any other problem with them. So far so good. The new prom works as expected, but the board is not yet starting. Also, the RAMs are connected to the original failed ICs L11 and N11. This pin looks like floating. Pin 12 of the N14 RAM is an output pin and is connected to N11. Since the RAMs have the output control always asserted, that pin should not be floating. So I took the other two RAM ICs and tested them on the Tilegunner clone, and they are still good. This is again the updated failure map. The N14 RAM IC was connected also to N11, as we have seen. At this point, checking on the ICs directly connected to the failed ones started to show no evident problems. And I've spent a few hours checking various points in the circuit, going progressively away from the big failure zone. Then some very lucky thing happened when checking the multiplexer ICs that connect either the primary or the secondary accumulator to a common data bus. This pin is really floating. Now pin 6 of T2 is an input coming from the primary accumulator, and I verified it to be good. So it was only a bad socket contact. Again, this might be because of all the PCB handling back and forth to remove and socket the failed ICs, so I just installed a new socket for T2. Then I also decided to change the IC, since it had corroded legs and I've noticed it was slightly warmer than its neighbors. This made me look at its outputs too. This looks okay. But on pin 12 the high level is really marginal. Pin 12 of T2 is driving only two inputs, pin 15 of M9 and pin 2 of P9. This time I'll use the current tracer instead of cutting pins. Here we see the high current at the output pin. but on M9 we don't see any high current flowing. So sure enough, pin 2 of P9 shows the high current, so this is the bad one. Now P9 is the only IC that is not directly connected to any other IC that failed. This is really puzzling. Before installing the new IC on P9, I've checked again the output pin of T2, and this time the high level is correct. P9 replaced, let's power on. Yes, it started! It's over, it is starting, yes! I have reconnected the video output and all seems okay. It is really hard to reconstruct what initially went wrong on such a large failure, unless of course something really bad happened on the power supply, but I can really exclude this hypothesis. I can only think about a chained failure, but also that seems unlikely to me, because for some reasons N11 and L11 had the biggest internal failures and must have failed together. Then S13 that drives inputs on both of them is likely to have failed too. And so also the other ICs directly connected to either N11 or L11 failed. And in this scenario, U11 must have been killed by the death of S13. I don't think S13 could have started all the chain, because it's a driver for both L11 and N11 inputs, so a driver seldom can cause a failure on a driven IC. However, also the fact that two separate ICs must be failing at the same time is very unlikely. I clearly remember that the board failed when it was running in attract mode, and I think the broken crystal pin may have caused a sudden clock failure of such a large scale that many ICs had abrupt changes in their current consumption, so that the trace inductances started to produce voltage spikes to counteract the current changes, and these transients were enough to cause some failures, even if the board has plenty of bypass capacitors on the power rail. Anyway, if someone has better ideas, please share them in the comments section. At this point, the board worked for a few days without any problem. So, it's all for this video. I hope it was interesting and that you learned something. Have a nice time and thank you for watching.